tell me which cosine identity you're looking for?
So it's the problem was ej2 omega plus ej omega plus 1 over
ej of omega plus
ej2 omega plus ej omega plus 1
plus 1?
over the same thing with a 2 on the middle term, on the j omega.
All right.
No.
What?
The same thing. So ej2 omega plus 2 ej omega.
Hold on. What comes next?
Okay, so the top term is ej2 omega
Hold on.
plus ej omega plus 1. And the bottom term is ej2 omega plus 2 ej omega plus 1.
Is that it?
Yeah.
And you want to turn this into cosine?
It turns into 1 plus 2 cosine omega over 2 plus 2 cosine omega.
I'm going to tell you, normally when you're doing this, if you want to turn anything into a cosine, the top part is what did it turn it into?
1 plus 2 cosine omega.
Moves by what? E by minus j omega.
There's a lot of ways to turn these into anything you want. Keep in mind the identities. Cosine of really I put omega is equal to e to the j omega plus e to the minus j omega over 2. All right? All right? That's one thing. Now the second thing is if you have e to the j omega, that's equal to what? Cosine of omega plus j sine of omega, right? Depends how you want to do this. If you want to try to make it fit this form, you can do it that way. If I factored out, just here, if I factored out e to the minus j, I could factor from this one and this one, e to the minus j omega, or actually I could get this one and this one, I could get a cosine easily out of there. And then I could probably mess with that. Now, this might be an easier route. Just use this identity on top and bottom. If everything's in terms of cosine, is it?
Yeah.
No, but
Yes.
You can use this identity because he wants it in terms of cosine, right? And the signs will cancel probably, right? You're going to see this happen. I'm going to just do this once. I'm not going to play around with this very long. All right, so if I do that, then this one would turn into be what? Cosine, right, of 2 omega plus j sine of 2 omega, right? This one is what? Plus cosine of omega plus j of what? Sine of omega, right? And then plus 1 here. Downstairs, this is cosine of 2 omega plus j sine of omega. Then you can go plus 2 times the quantity cosine of omega plus j sine of omega plus 1. Now just put them all down like that. You don't have to worry about this. This is not the focus of the class. This is one of these things that just teaches you how to manipulate things. All right, this is not a big deal. But if you get down to this part, you can use that identity. Cosine of 2 omega is equal to what? Isn't that what?
2 cosine of omega square minus
2 minus what? What's that again?
2 cosine omega square.
2 cosine square, cosine, oh, it's, pardon me, 1 minus cosine squared of omega, right?
Yeah.
And isn't that right, class? All right, now, you can do that. You can replace this one here and this one here. I'm just going to tell you, this is one of these things you can manipulate this with this one. Just follow me. This identity right here,
That's not right.
what's not right?
That identity. It's 2 cosine squared minus 1.
Wait a second. Cosine of a, or 2 theta, right?
Yeah. Cosine of 2 theta transformature is equivalent to 2 cosine squared minus 1.
You're right. Yes, you're right. 2 cosine squared of omega. You're right. Minus 1. I stand corrected. Take that, and if you stick that in there, you're going to probably see everything cancel but the cosine and the 1. I'm just telling you, this is one way to do it. And same with downstairs. Now, the way that I do this, I don't play a lot around. It doesn't buy you anything to mess with these too much. If you take a look at this, and I want to do things, I can do one of two things. If I look at these 2 terms right here, right off the bat, I factor out And it depends, is the argument in terms of cosine omega?
The answer is.
All right, then I can't do it on those two. You're manipulating the wrong one. If it's in terms of cosine omega, if I take this and this term here, and I factor out an e to the j omega here, now I have e to the j omega plus e to the minus j omega, right? Right? Now, I can easily turn that into a cosine, 2 cosine of that argument. So now I check this box and this box, and I have an e to the j omega. Do you follow me? Let me just work with this top part. You'll see this. If I start here and just work with the top part, these two give me e to the j omega, and then this is going to be 2 times cosine of omega, right there. That's this one and this one. Now I have plus e to the j omega, right? Left, correct? On top? Now factor out e to the j omega. Now I have e to the j omega here, and I have 1 plus 2 cosine of omega on top, correct? Now go down here, take these two right here, and go ahead and do the same thing. You're just going to see it's going to come down, and it's going to basically, this is going to be what? You factor out e to the j omega, right? If I factor out e to the j omega, I get what? Down here, I get e to the j omega, right? Plus e to the minus j omega, right? And then I have plus 2 e to the j omega, right? That's going to be 2 cosine, right? Isn't it? And then I'm going to have this and this as well, right? So I factor out an e to the j omega, correct? Then, yeah, I know. You're going to cancel e to the j omega. And now I get out of there what? I have the 2 cosine, right? Of omega. And I have plus 2. Don't I? And the e to the j omega cancels. I don't know if that's the form he has, but that's, you're really just fussing around stuff and you're wasting your time. Once you have this right here, in terms of what we're after, that's it. Really, because you can get the angle, you can get magnitude and phase from that. That's all you're after. So they're just fussing. Any other questions about the homework? All right, last class period we covered quite a bit and went through everything I think you need to know about that. Today what I want to do is go through, this is the discrete time Fourier series analysis, and I want to spend a little time contrasting everything today. This is the part of the course where I try to link everything together so you see the interaction, how you can basically use the manipulations in Laplace and Fourier continuous time transforms to understand discrete time even with a DFT, and we'll get to an FFT probably in the next class or two. The fast and zero value. So first of all, this is going to be for series, this is going to be for periodic functions. And this is a review. All right, now, when you remember if you had a periodic function in continuous time, something like this that repeated itself, you know, just repeats itself. There's a fundamental period, T naught, or T that you had to find, that's the period, this is time here. And this is going to be x of t, right? Now it's a periodic function. It's like a power function. It has an infinite amount of energy and a finite amount of power. When we have this, we found out that we could say the x of t here, because it is periodic, could be rendered as an infinite series, where n went from minus infinity to infinity, right? Of the value c of k times e to the j n omega naught t. And we know that omega naught here was 2 pi over the period t. And t is called the fundamental, right? Really, 1 over t is the fundamental frequency. Let me put it that way. 1 over t is referred to as f naught, or the fundamental. Fundamental frequency. And that's in hertz. 2 pi times that, yeah.
What's that on the top of the summation? Is that C naught on the top?
This?
Right
That's
there.
infinity.
Oh, that's infinity. Okay.
My infinities are not infinities. They're meant to be, but sorry, they don't render well. All right, you follow me, everyone? Now, remember how we got C of k for this one. How did we do it? Anyone? We had 1 over t out in front, right? That's a scaling thing because we're going to do something. We're going to integrate over t. we're going to integrate from 0 to t or over any period. I actually like to go, if possible, from minus t over 2 to t over 2. Usually that takes care of any transitional problems. You don't want to end on a transition if we do the derivative method. Do you remember how we're going to do that, ultimately use the derivative method when we have this class? If we can, right? But this is the more basic thing. This is the general formula. And then it's times x of t here times e to the what? Minus j n omega naught t dt. And that c of k goes here. And this is an infinite series that approximates, or actually, to a high degree of exactness, it replicates this, except when there's a discontinuity. At the discontinuity, there's something called the Gibbs phenomenon, where it'll go to the value, the average value of just before and just after the discontinuity. Do y'all remember this class?
Yeah.
Now, we can also go a step further. I can say I could turn this into a single-sided cosine series. Do y'all remember that? This is a bit of a review. I could do it. I could say that this entire series x of t here could be rendered as C0, that's the average value, plus the summation here from n equals 1 to infinity of 2 times the magnitude of c of k, or c of n, pardon me, c of n. I should have put n here, not k, my bad. That's supposed to be c of n, not k. 2 times magnitude of c of n times the cosine of n omega naught t plus the phase angle of c of n, right? And that's a single-sided cosine version of this. Again, this is for continuous time, and it's periodic. Now think about discrete time and analogy of this. In discrete time, we would have a function, I'll stop here, we would have a function x sampled of t would be equal to x of t times that crazy summation of delta of t minus nts, right? N goes from minus infinity to infinity, and basically we sample now x of t at singular values, at nts. Now we have a infinite discrete series, not continuous time. Follow me? And there's a sampling frequency. What it looks like is this, and I'm going to try to be as exact as I can about this. There's going to be something, and call this now n. We're not going to do it in the time axis, but an n-axis. So we take out ts. Whatever the actual sampling interval be, we forget about it. We take a look what it might look like. And it might look like this. I'll have a sample here, a sample here, a sample here. Then it'll go to 0. And then a sample here, sample here, sample here. And then 3 more zeros. And then it's going to repeat itself.
Hey, for that excess, would it be excess
Hold on for
of
1
n?
second. X of n. Here. What?
I was just, would that excess be excess of n or excess of t?
No, it's still, well, look, it's a function of n here, right? And it's a function of t here. There's still t in the argument, right? But now this is a sampled version of the signal. This is an infinite series, so n itself doesn't exist when you do the sum. What it's basically doing is extracting the values at an infinite number of points. You follow? You sum out on n. It's not there anymore. All right. Now the truth is, once you do that, then you can actually say, we can keep going on this, and you're right, you can get it down to, you basically are going to have an x of n. I didn't do this yet, but you have to, you're right, you're ahead of me. It's going to become now, we're going to say, because this is only for discrete time values that are non-zero. This is for all time, right? But the only values that are non-zero will be the ones where nts occurs, right? Where it's basically nts, all right? And that means you can just say, yes, we're going to have a function x of n. And that's going to be this right here. Now, what I'm showing you is something where this would be like 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, and that's just n. Now, the fundamental frequency, or the fundamental number, in our case, is going to be really associated with the period from before. If you look at this, how long does it take before it starts replicating? 0, 1, 2, 3, 4, 5, and then replication, right? So from 0 to 5, n naught, it's called, would be 6, right? Because there are 6 discrete values before it starts replicating or repeating itself. Does everybody see this? Give me a show of hands if you do. It's identical to this, the period. Only now this thing is sampled, you might say. It's sampled, you know. here, here, here. All right, class? So if we have something like this, and this is admittedly crude, and it's in your book, can you tell me what page the discrete time Fourier series is on? I know it's towards the very end of that chapter 7. 389? And it'll say discrete time Fourier series, or discrete, I think it's discrete time Fourier series is what he's going to have in the book. Another book will state this a bit differently sometimes. Follow me? Again, it's periodic, but it's discrete, not continuous, not like this stuff. That's continuous, all right? Now, we take a look at this right here, my x of n. I know I have an x of n, but now I say that x of n can be rendered as this, and it's exactly the same principle as this. I don't want to go through, there's a thing where you can do the entire proof. I can take this, literally, and stick this in here, right? And I can get a value for c of k, it'll be a discrete number, and then I can put that in there. But I'm going to get right to the, cut to the chase of this. What this will amount to is now we're going to have a series here, n equals 0 to infinity, actually from minus infinity to infinity. I think it's in his book from minus to infinity to infinity. And now it'll be of c of k here, and it will be e to the j 2 pi over n naught to the nk. It looks a lot like a DFT. Take a look at your book for a second and confirm that that's what it shows. You have your book open. Do you see it right there?
It says from 0 to n naught minus 1.
All right. Oh, I'm sorry. I'm sorry. Absolutely. No, the series for x of n, not c of k.
Yeah, it's still.
He's going to have for c of k this, right? He's going to have c of k being equal to 1 over n naught, right? And then he'll have the sum from n equals 0 to n naught minus 1 of x of n here. It'll be times e to the minus j 2 pi over n naught nk. Do you see this right here for c of k? Do you see it in your book? Okay. No? Yeah. I'm sorry. Borrowed somebody's book.
Definitely says that for x of n.
Here. He's going to have, he calls it x of k, my bad. And he goes from 0 to n minus 1. Yeah, okay. My bad. Actually, what I've got here is something. This form is not the reduced form. What he's going to do is say, because of periodicity, even though that's true, this is really going to be because there's just, because it is periodic. What it amounts to, what I put down there was correct. But the thing is, because it's periodic in 2 pi over n naught, he's going to have it from n equals 0, or k, sorry, k equals 0, and it will be to n naught minus 1. That should be what he has, basically. Now, he calls it x of k, though. Is that right?
Mm-hmm.
All right, my bad. X of k right here, and this would be x of k. And that's saying the same issue. K goes from 0 to n minus 1, right? N naught minus 1. Do you see that in your book, guys? Anybody else have a book open? Isn't that what he has?
Mm-hmm.
Now, listen to me. I'm sorry. Look, when you looked at this one before, this went from minus infinity to plus infinity, right? And the reason that's the case is because this frequency domain is something that goes on forever. Because there's a discrete number of samples. And you remember with the DTFT, it repeats itself every 2 pi, or DFT, it repeats itself every 2 pi points. Here it's just 2 pi over n naught times nk, and that looks very much like a DFT. Let me just say one other thing about this right here. If I look at an actual DFT of a signal, if I look at x of k, do you remember what that is? For the DFT, that was what? The summation of x of n, right, times e to the minus j 2 pi over n to the nk power from n equals 0 to n minus 1 points, right? Isn't that what it was, class? Do y'all remember this? Well, look at the difference. The only thing is, this is a scaling factor. It's the same thing. Y'all see this? There's only a 1 over n there, and that 1 over n comes from this right here. The scale factor here, so that you can write a series just like this. Now some books put the scale factor over here in front of this term. It doesn't matter where it goes. The scale factor is just 1 over the n naught. So if this is a DFT right here, it's nearly identical to that, which tells you something. All right, what do you remember about a DFT? Do you remember how you could take a DFT and you could modify it by multiplying it by that 1 minus e to the minus j omega over j omega and multiply by for the x of k, and you could actually get the Fourier transform? How many remember that? You don't have to remember everything, but you actually did an extra credit on that. Do you remember doing it? How many do? All right. What is that? That directly compares it to the Fourier transform, doesn't it? Same thing you can do here, but instead of the Fourier transform, it directly compares it to Fourier series. All right, because this is, we compare it to the Fourier series of a continuous time function. That's the difference. Remember, Fourier transforms are for energy, Fourier series are for power signals. That's one of the things you keep in mind. All right, so basically with this, if we wanted to calculate something in the back of his book, he gives a few problems, and I had some of the problems written down. I want you to just focus on these two for now, and remember how close they are to the DFT. If you look at those two for a second, and we just calculate it for a single thing. And he's got some in the back of his book. He just wants to get you familiar with this. I gotta say one other thing. This is for really, I'll call them energy signals. This is for power signals, or periodic signals. So keep that in mind. Now, I mean, what this basically said is this is the total number of points, it's capital N, period. Everything else was 0 assumed, right? And here, we don't assume it's 0, we assume it's periodic. And that, therefore, the weighting factor, 1 over n naught, to get the average. All right, now, suppose you have this, just as something. I'm going to just show you the kind of stuff in the book. Suppose I have, this is going to be versus n here, and I'm going to have this. 1, 2, 3. This is going to have a height of 2, height of 1 here, and then 0, and it repeats itself. And so forth on here. So this would be n equals 0, 1, 2, 3, 4, 5, 6, 7, and so forth. And this is going to be x of n. It'd be better if I had graph paper to show you this, but you follow me. I take a triangle wave and I just sample it, right? That's all I'm doing. And I'm showing you discrete points. So the first thing you have to do is look here, and what is the value of n naught? How many samples before it repeats itself?
6.
Well, let's see, you got 1, 2, 3, 4, 5, 6, and then it starts over again, right? So it'll be 6. Now, next, when you look at the values here for x of k, all right, x of k by definition, or, yeah, that's equal to 1 over 6, right, times the summation here of x of n times e to the minus j, and it's 2 pi divided by 6, or really pi over 3 to the nk power, n equals 0 to 5. You're going to sum starting at 0 to 5. So what is x of 0 going to be? Just look at that and tell me. If you're asking for x of 0, what are you doing? What's this value right here? E to the minus j pi over 3 nk.
0, 1.
Here here k would be 0, correct? And 0 there means that's just 1, correct, class? So it's just the sum of all the values divided by the number of values, or the average value, isn't it, class?
Yeah.
It's just like C0 was in the continuous time Fourier series. So here that's 1/6, and just sum the values up. 1 plus 2 plus 3 plus 2 plus 1, right? Or you have 3, 3, 3, right? 9 6, right? Or 3 halves. It's that easy. Now, if you wanted x of 1, what would it be? Well, now it's going to be 1/6 times the summation here of x of n, and it's going to be times e to the minus j pi over 3, right, to the nth power, where n goes from 0 to 5, right? Now, what is e to the minus j pi over 3?
J root through 3.
That's what? Cosine of pi over 3, right? Minus j sine of pi over 3. What's cosine of pi over 3?
1/2.
And? Right. Minus j. You can leave it like that. Or you can really, if you want, you can leave it like this and just see how things work out. You probably get a cosine out of it, or sine. You follow me, class? All right, so if you wanted to do that one, what would that be? That's 1/6, right? First value, that's when n is equal to 1, right? And it's going to be 1 times this is going to be e to the minus j pi over 3 plus 2 times e to the minus j 2 pi over 3, right? That's a 2. Plus 3 e to the minus j pi plus 4 e to the minus j, what? 4/3 pi, right? I mean, not 4, 2, pardon me, 2. And then plus 1 e to the minus j, what? 5/3, right? Pi. And you add them up, right? So then I'm just showing you, trying to go through the, at least a way to look at it and figure it out as you can as quick as possible. First thing I'm going to do is say, what is this number? E to the minus j pi is, class?
-1.
It's -1, so I can get rid of this and just put down minus here. Do you agree with me, everyone? I'm just trying to simplify. Now, if you have a calculator, you can do this fairly easy. Next thing I'm going to do is see if I can get a sine or cosine out of there. And when I look at this, I have e to the minus j pi over 3. Let me try to do it this way. That would be 60 degrees, wouldn't it, class? Pi over 3, right? Next one is what? I got that, and I have e to the minus j 5/3 pi. And that's here, isn't it, class? This would be 5/3 pi. That's this one. You all follow me? Now you see that cancels that? Did y'all see that? So cancel that one and cancel this one. Now what about these two? I've got a -3. What happens there? This might be a little more work than you signed up for. What is e to the minus j 2 pi over 3? Isn't that 120 degrees, class? Isn't that right? So where's that vector-wise? Here, right? And it has a length of what? 2, doesn't it? So that's 2 here, and this is at 120. And what's this one? Where is it? Well, if it was 3/3, it would be 180, right? 4/3 would be what?
Also 120?
It would be right here, wouldn't it? And this would be -120. Do you agree with me, everyone? Right? And what happens? The vertical components cancel and the horizontals add. So if this is 120, that's still 60 degrees there, right? The cosine of 60 is 1/2 here, right?
Yep.
When you add the next one to it, it'd be cosine of 1/2 times that. Since the length of this is 2, the projection is 1, projection is here is 1, correct? So that would be -2, would it not, class?
Sure.
You follow me on that?
Would minus j 4 pi over 3, that be in the second quadrant because it goes.
What's e to the minus j pi? Isn't that -1? That's 3 over 3, right? 4 over 3 is in the third, right?
I think you're doing the
Yeah, would it be, cause we're going,
It's negative.
Clockwise.
Jay.
Oh, you're right,
But
you're right.
you're right, cause they're.
There will cancel, it does effectively do that, you're gonna get cancellation of the vertical component. Alright, I'm gonna just stop here with this one, but this is the essence of what you do. I picked a bad example because it's got too many crazy possibilities. Usually there are four values that you would get when you do this, but discrete time Fourier series is really something to understand when it comes to power signal representation of things. Now, a lot of that has to do with Wi-Fi, because with Wi-Fi signals, they are continuous, more or less. So just remember that. I'm not too worried about that. I wanted to mention this. Now, one last thing. Now what I'm going to do is try, this is one part I wanted to get to. I'm going to try to show you and really the similarities and equate everything we've done as best I can. We started with convolution. So we said in general, if you have two signals x of t convolved with h of t, by definition it was the integral from minus infinity to infinity of x of either tau or lambda times h of t minus tau d tau. That's the definition, and these are interchangeable. We knew that. We know what convolution is. You basically take one signal, thing that has the most going on, you leave it alone, you flip the other one, you shift it, and you multiply both functions together in the overlapped area, and then you do an integration of that, and that is what the convolution of the functions are, and that's the definition of it right there. When we had convolution, for discrete time signals, we had x of n convolved with h of n, and we found what that boiled down to was a summation, right? And the summation was an I, usually it starts at 0, technically it can go to infinity, this could be minus infinity, but usually of 0, and it's going to be x of I times h of n minus I. Now you can switch these, right? That's discrete time convolution. We do both of these. You're responsible for both. After that, we did Laplace transforms, and we started and we said that x of s, this is for energy signals, by the way, usually, x of s was equal to the integral from 0 to infinity of x of t times e to the minus st dt, and that was going one way, and technically we could get x of t as 1 over 2 pi j times the integral from minus infinity to infinity of x of s times e to the st ds. But we never really did this, did we? What we did is partial fraction expansion anytime we wanted to find x of t. Do y'all remember that? And we knew the basic transform pairs. This is important. And the basic transform pairs are like for the delta function, it always goes to 1. We knew that if we had like x of t here goes to x of s here, we knew that a to the, or really e, I think they have in the book, if we have e to the minus at u of t, that goes to 1 over s plus a. If we have u of t, it goes to 1 over s, these are the most common, and so forth, and then we use properties to get the rest of them, but that's Laplace transforms, and you have to make sure you have a clear understanding of Laplace. After that, we went to Fourier transforms, and we found out that x of omega was equal to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt, and we had x of t equal to 1 over 2 pi, the integral from minus infinity to infinity of x of omega times e to the j omega t, the omega. This was termed analysis, and this was synthesis. Because we could create filters and so forth and look at the actual impulse that would result, the impulse response that would result. And there was one particular thing about this, that was two actually, that were really important. One was that x of omega was equal to s equal to j omega. This is the Laplace transform. If x of t equals 0 for t less than 0. So that was real important, that you could literally take the Laplace transform and simply replace s by j omega, and you could get the Fourier transform if x of t was in fact 0 for t less than 0. Do you all remember this, class?
Yeah.
This is real important that you keep this in mind. Now, all this is continuous time except for this part right here. Then we go into the last part for continuous time. That's Laplace, that's Fourier, and we said that if we had a periodic signal, something that was periodic like this, and period t, we just did this, and this was x of t, then x of t could be rendered as an infinite series from n equals minus infinity to infinity of c of n times e to the j n omega naught t, where omega naught here is 2 pi over t, and c of n was 1 over t, the integral from minus t over 2 to t over 2 of x of t times e to the minus j n omega naught t dt. We could do that, and we usually use the derivative method to find the actual value of the c of n. That was typical. C0 in this one you have to know though. C0 is 1 over t times the integral, really from 0 to t of just x of t dt. It's the average value of the signal. And we just did put it in terms of a single-sided cosine series, right? We did all that. Then, that's basically all continuous time except for this point right here. Then we moved into discrete time. And the first thing we did in discrete time is the dt ft. It's very similar to the discrete time Fourier series that we just talked about, right? For the discrete time Fourier transform, we had x of capital omega equal to the summation from n equals minus infinity to infinity of x of n times e to the minus j n omega. And by the same token, we had x of n equal to 1 over 2 pi, the integral from minus pi to pi of x of omega times e to the j n omega d omega. And here we use duality. Make a note, duality, to get that value. This is important that you write this down. You're going to see a lot of this later. Now, at that point right there, then we moved over when we did the DFT. And that took this and reduced it in terms of the actual number of terms, right? And we had x of k equal to simply the summation here of x of n, and this is something we just basically did, 2 pi over n to the nk, where n equals 0 to infinity, or 0 to n minus 1, pardon me. And I'm going to stop there, but I'm going to write down all this linkage, and we're going to actually go from Z transform back to Fourier's, the actual Fourier transform in a bit. But I'm